Hello everybody. I'm going to present you the LUR project in which my thesis is involved. This project is financed by the region Auvergne-Rhône-Alpes. So my presentation will be articulated in the following way. First of all, I will talk about the context and the objectives of the project. After, I will present you the results that I have obtained during my first years of PhD, and I will finish by a little conclusion. So the entry counterfeiting cost to the European economy billions of euros. No sector is spared. It is necessary to develop reliable, high security, low cost, and easily controllable solutions at any time of the product circulation chain. So the LUR project is an answer to this problem by seeking to combine two known technologies, the luminescent coating and the resonant gratings. This new technology would be expert markers because it's combined two markings with an interdependence never explored to our knowledge. So this association will exploit several optical effects depending on condition of observation, like the resonance here and the emission of the luminescent coating. But to do this combination, we have to respect several criteria in the development process. The optical properties of the luminescent coating and the resonant grating do not hinder one of the other of the system. It's important to ensure that the different coatings adhere to each other. The embossing must be possible on the salt gel we used, and the salt gel used have to be homogeneous dispersion of the luminophore. And we need to control the refractive index of the different layers. So first of all, I will start with the fabrication of the luminescent coating with the commercial organic chromophore, the rhodamine B. So we begin with an optimization of the luminescence of the rhodamine in the ethanol. After that, we focused on the formulation of our dispersion medium, namely a TeOS-MTeOS mixture, based on the literature data, and after several adjustments on the ratio of the precursor, we found a formula that allows us to obtain by spin coating the desired thickness. So we worked on a mixture of TeOS-MTeOS rhodamine, just here, at different concentration. On this slide, you can see the absorption spectra of the rhodamine in ethanol and in the mixture of TeOS-MTeOS. And we show no influence of the mixture on the absorption of the rhodamine. So we study the mixture of TeOS-MTeOS rhodamine to determine the best concentration to obtain the maximum of luminescence. On this slide, we present the evolution of the absolute quantum yield of photoluminescence for 3 excitation wavelengths as function of the concentration of the rhodamine. For the 3 wavelengths, we pass by a maximum for the cell having this concentration, and that result is confirmed by the emission spectra at different concentration, and we find the best luminescence for this concentration. After that, we optimize the deposition parameters to obtain a transparent layer with a thickness around 200 nanometers. The emission spectrum of this coating is present here. We saw shift of 13 nanometers, which induce a different color of the rhodamine in solution, but is not problematic for our application. So now I will present you the resonant grating. So a resonant grating is a structure composed of 2 elements, a sub-wavelength diffraction grating and a waveguide. The principle is to trap the incident beam in the waveguide via the coupling and decoupling of the wave in the diffraction gratings. The resonant grating will resonate to a specific wavelength of the gain mode, and it's sensitive with a lot of parameters that you can see in the slide, like period, incidence angle, etc. So the goal of your project is to combine the luminescent coating with the resonant grating. For this, we have imagined this design where the grating is embedded by the luminescent coating. So we have SiO2 topped by a thin layer of high-index TiO2 that follows the shape of the gratings, and that follows the shape, and the wall is covered by a luminescent coating. The simulation we performed to optimize this design, and we fabricated this design with these parameters. Here we are looking for two effects, luminescent and resonance, what you can see just here, and it's a two independent effect. On this slide, the simulation, we try to observe the resonance with a maximum different from the maximum of emission of the rhodamine. We have chosen arbitrarily to be positioned at an angle of 0 degree, optimizing a resonance in the green. So the simulation gives us a resonance at 500 nanometers. It's an intense one and not too faint, allowing us to observe it. And we can see the resonance shift as function of the incident angle. The resonances are thinner and with less intensity, so less visible. Before I introduce you the results, I present you the process of fabrication of the design. We begin with the fabrication of the grating by interferential lithography. After that, we create a mold in PDMS of the grating for embossing a SiO2 layer. We can depose after that TiO2, which is the waveguide of our design, and we can finish with the luminescent coating presented before. So here we have the sample we obtained. We chose to make a logo in the grating to highlight the resonance. This spectrum presented here shows the superposition of the experimental resonance and those obtained in the simulation. So we observe a slight shift in wavelength due to experimental errors. And this 2D map shows as the simulation the shift of the resonance according to the angle of incidence. Donc the measurement and the simulation we optimize with a TE polarization because with TM polarization, the resonance peaks are thinner and therefore not visible like you can see in this picture. So to conclude, we have succeeded in optimizing both technologies, the luminescent coating and the resonant gratings. We also succeed in showing that the two techniques are compatible with each other. The next step will be a design with a result we can observe the resonance and the luminescence of the sample. A larger number of optical effects and colors are obtainable with the design, so we can imagine a large number of optical combinations. Thank you for your attention.